The topic is representation of graph. What are the various representations of graph? One is using array representation, that is the underlying 2D array is being used, that is called adjacency matrix. Another is using that help of linked list, that is called adjacency list representation. Both these representation can be used for directed as well as undirected graph. That means within the memory, either you can take the help of linked list for storing the graph, or you can take the help of arrays for storing the graph. Now, the adjacency matrix. Adjacency matrix is basically a 2D array where your representation of graph is being stored. Like if you are taking the example of this one as a undirected graph, here if you see it is will be there are 4 vertices. The matrix 2D matrix of will be of 4 by 4 here, and this will these ones will tell the connectivity adjacent to, like 0 is adjacent to 1 and 0 is adjacent to 3. Accordingly, in the 0th row, 0 and 1 entry will be done for the 1 column index column, and 1 entry will be done for the 3 index column. Similarly, if 2 is adjacent to 1 as well as 3, 2 is adjacent to 1 as well as that of in second row, you can index row, you can say 2 is adjacent to 1 and 2 is adjacent to 3. Remember that this in case of undirected graph, this adjacency matrix is a symmetric matrix. The reason being, if I'm saying 1 is adjacent to 0, 1 is adjacent to 0, it implicitly means that 0 is also adjacent to 1. That means it is a symmetric matrix in case of undirected graph. In case of directed graph, it is asymmetric. That means it depends upon the edge only. Like 0 is adjacent to 2 and 0 is adjacent to 1. The entry for will be 0 to adjacent to 1, and if 0 is adjacent to 2, this entry will be equal to 1. But the reciprocal is not same. 1 is not adjacent to 0. So 1 is not adjacent to 0. That is why this entry is 0. So 3 is adjacent to 1, so this entry will be equal to 1. 2 is adjacent to 1, so this entry will be equal to 1. This column, this will represent the adjacent two matrices. So these are the set of edges and these are set of vertices for the same. So this is, if you just go for the definition part, that this is the matrix of a graph G, which consists of set of vertices and set of edges, is a two-dimensional matrix of size V cross V. That means the size of that matrix will be the number of vertices in the graph multiplied by again the number of vertices. That is equal to V square, such that each entry of the matrix is equal to 1 if there exists between Vi and Vj, otherwise it is equal to 0. If it is a weighted graph, then other than one entry, the value of the weight will be given represented at the respective row column junction. Now, what is the degree of vertex in case of if you are using adjacency matrix representation of graph? Now, in this case, this is the example for a directed graph. In directed graph, if you carefully see what is the in degree of this C. In degree means incoming edges into the vertex C, that is 3. So if how to find the in degree of graph of a vertex within a graph, just found the number of columns within that column C, the number of ones. The number of ones here are 3. That this will represent the in degree. That means sum of ones for a given column will give the in degree of that respective vertex. Similarly, if you go for the out degree, here out degree is 1. That means sum of the ones in the for that vertex C within that row, that represents the out degree of the vertex. So out degree in the terms of number of one, that is a row sum within the for a particular row, find the number of ones, and for in degree for a particular column, find the number of ones. Now, in case of undirected graph, that degree is nothing but it is simple degree, that is either in degree or out degree. You can, for let us suppose for vertex index 1, the number of ones in horizontal row and number of ones in the vertical for the same index column will remain the same. That means both are 2 because of the concept of undirected graph. Next comes weighted adjacency matrix. If the graph is weighted 1, So rather than the value of entry being 1, that value will be other than value of 1, that value will be given the will be substituted as a weight of that edge. This graph in this case will be symmetric one. That is, if your entry is 2 to 14, the entry is for 2 to 4, the entry will be weighted graph. Weight has got 13 unit. Now, in this case, if you want to find the degree, if you want to find the degree in this case of weighted graph, count the number of non-zero entries. That will give you to the in degree of that graph. If you want to vertex, if you want to get the out degree of vertex, say that of 2, you can go for the number of non-zero entries. Now, in this example, because it is undirected graph, that out degree and in degree will be same, that will be equal because of the symmetric nature of the graph. What are the pros and cons of adjacency matrix? No doubt it is simple to implement, and it provides order of one, that is constant time, to find whether that edge exists between any two pair of vertices. If the value is 1, then between the edge say C and A, the connectivity edge exists. If the value is 0, the edge does not exist. Just by merely checking the value at the particular row and column junction, you can find whether edge exists between those pair of vertices or not. But the main drawback of adjacent matrices, it takes order of v square amount of memory. Now v is basically the count of the vertices. If I have got 10 vertices, it will take 100 capacity array, that means 10 by 10 array, for storing the adjacency of the vertices with each other. Now in weighted graph, it is good way to represent weighted graph using adjacency matrix. We merely have to put the weight other than the values of 1. For like weight can be from distance and cost. Second representation of the graph in memory is that of adjacency list. What is basically the adjacency list? It is nothing but it is a collection of different linked lists, and like this is the one linked list, another linked list, and so on. And the starting address of that linked list is nothing is stored in the array. It is an array of basically collection of addresses where every address points to the starting address of different linked list. And single node in the linked list represents the, say for the vertex index 2, the 2 is adjacent to 0, 2 is adjacent to 3, 2 is adjacent to 4. So in the second index, the starting address of that linked list will contain the data portion. 2 is adjacent to 0, 2 is adjacent to 3, 2 is adjacent to 4, that is data portion, and pointer to the next node within that linked list. This basically, if you say for the number of nodes in the undirected graph is basically equal to 2 times of count of edges. The reason being, in this case, if you go for this example, the number of nodes for this in this case will be 2 times, because there will be double entry for 0, 1 as well as 1, 0. If you just carefully note, these are the number of nodes in this, not in the undirected graph. Number of nodes in the linked list representation of adjacency list, the number of nodes will be 2 times the count of edges. If there is a edge 0, 1, that entry for 0, 1 will be this node, and similarly the entry for 1, 0, that will be this node. That means it will be 2 times the count of edges because of the symmetric nature of the directed graph. Next is your for directed graph, what will happen? There will be unique entry. Now the number of entries, like basically these nodes in the linked list representation, that will be exactly equal to the count of edges. Like 1 to 2 there is an edge, 1 to 2 there is an edge, 1 to 3 there is an edge, 1 to 4 there is an edge. So this will be adjacency matrix will be from this representation will give me the adjacent two nodes. Like if you are taking example of say 5 is adjacent to 2, so the entry for 5 index starting address array will have linked list node pointing to the 2 node. Similarly, for 1 is adjacent to 2 and 3 and 4, so in that case, pointing to the starting address for one node, this will be linked node will be 2, 3 and 4 and so on. Because 4 is pointing to itself, the node will be this one. Next comes the degree of a node. What is degree of node in case of adjacency list? How to find? Degree of node is basically the count of edges. If I say what's the degree of this node 0, you merely count out the number of nodes in the linked list pertaining to the 0 index pointer within that array. So this the count is 4, the degree of this is node is 4. Similarly, if we want to find the degree of say node 2, this is equal to 3. If you go for this, the number of nodes in the linked list pertaining to the second index array pointer, then that will be 3 nodes. For undirected, for directed graph, the degree will be, this is will call out degree. Out degree means if I want to say what is the out degree for the node 1, there are 3 nodes. Out degree of this is 3. This represents the out degree of a node. Similarly, if you want to find the in degree of particular node, in degree of node 2, say for that particular case, in degree can't be directly calculated. For that, you will have to scan for the vertex index 2 every linked list one by one. Now 2 is present here, then 2 is this is the array of pointers. Basically, this first go for the linked list pertaining to the first pertaining to the adjacent to vertices adjacent to 1. The linked list, the elements is 2 here, one time more 2 here, another time 2 more here. That means there are 3 is the in degree of 2. You have to find the number of entries of 2 in the adjacency this linked list only. That means it is difficult to find the in degree of a vertex if you are using adjacency list, but it is easy to find the out degree. If I want to find the out degree of 1, I merely have to count the number of elements in the linked list pertaining to that one index array node. Okay, next is weighted graph. In weighted graph, if you want to represent the weighted graph, rather than along with that vertex which is adjacent to that particular vertex, like 0 is adjacent to 2 as well as 0 is adjacent to 1, there is one more portion within the node. One is called your vertex number, another is the weight of the vertex, weight of that edge from 0 to 2, and pointer to the next vertex, and so on. The adjacency list, the node will have basically 3 component: vertex of to which it is adjacent, weight, and the pointer to the next node. Now for example, 0 is adjacent to 1 and 2, and what are the weights of that? 0.2 and 0.4. So 0 is adjacent, node is adjacent to 1 and 2, the weights of that is 0.2 and 0.4. Similarly, 2 is adjacent to 3 as well as 1. So 2 is adjacent to 1 with the weight of 0.5 and adjacent to 3 with the weight of 0.1. So this is the representation, adjacency list representation for weighted graph. Now this is the representation, one example where this graph, this is undirected graph, this is the adjacency matrix representation, this is the adjacency list representation. For adjacency list, if you are doing implementing the same from implementation point of view, the node structure will be the v pointer and point to the next. If I want to take like this structure, so I can take 5 header pointers. It is an array of addresses basically, and every address points to the starting linked list address of that respective linked list. Now this is the example for the directed graph. This is not a symmetric graph because it is directed one. This is the adjacency list representation of the same, because like for example, V0 is adjacent to V1 and V2, so V0 is adjacent to V1 and V2, like it has been represented here. Now similarly, this is another example where which is adjacent to matrix is being given. Now coming to all these, after these examples, coming to the pros and cons of adjacency lists. Adjacency list saves the memory. The reason being because let us suppose your graph is sparse enough, it allows you to save the memory. Let us suppose I have got say 100 nodes. So if merely the connection between those are 3 or 4 edges are there, so rather than storing wasting such a huge amount of memory for the adjacency list representation, where only 5 or 6 are going to be ones, remaining are zeros, the better option would be adjacency list. Adjacency list utilizes the memory space efficiently. Then the time to check whether edge exists between the two pair of vertex in adjacency list is order of v plus order of degree of v. So this is basically order of v. That is the main disadvantage of this. For example, if I want to check whether the within given say whether the exist between say v3 and v2, what I have to do first, I have to traverse to find the address of starting address of v3 if it is being organized in that direction. Once if it is an array representation, this will take order of 1. If this representation itself is a linked list representation, which is the addresses starting address of the first adjacency list and so on, this is further a linked list, then it will take order of v time. If it is a direct array representation, you can take order of 1 time in that case. And finding further within this linked list, this takes order of v time. Reason being that depends on degree of this vertex v. Degree of 3, if its degree of 3 is 5, then 5 times I have to do comparison to search the index value, the value of 2, whether 2 exists here or not. In worst scenario, the degree of a vertex can be equal to number of vertices basically. That is exactly it can be at the most equal to v minus 1 excluding that vertex, or if it is there is a self loop, then it can be v also. So in that case, if you want to find the whether edge exists between two pair of nodes, at the most the complexity of that algorithm can be order of v. Now, if you go for space point of view, adjacency matrix goes for order of v squared space, and adjacency list goes for order of v plus order of v space. Now, order of v means that means the space required to store that arrays for the starting, which stores the starting address of every linked list, and the degree of vertex v1 plus degree of vertex v2 plus degree of vertex v3, and so if you sum up the degrees of every vertices, that is nothing but the count of edges. So it is basically order of number of vertices plus number of edges. Now, where adjacency list is being preferred if your graph is sparse. Sparse means where the count of edges is very less in comparison to the square of the count of vertices. Then adjacency list is the generally used one. On average, adjacency list is a method of choice. It is being used because of the efficient space utilization. But adjacency matrix is preferred only in those cases when the graph is dense enough. That means just like in case of complete graph, or where the number of edges are generally proportional to that is number of vertices squares. In that case, adjacency matrix is being preferred. These are some operations which can be applied either on directed or undirected graphs, as well as for adjacency list, as well as for adjacency matrix representation to find the degree of vertex, to find the number of edges in a graph, out degree of a vertex, in degree of a vertex, removing an edge or finding an edge or deleting an edge, adding or remove vertex, different graph traversals.